So as told, I'm M.Hazarika. I have done robotics and AI for almost 20 years now, and it is a great privilege to be here this morning. I shall discuss some research in the area of human-machine interaction, particularly for robotic neurorehabilitation and bionic prosthetics. Before I move on, I would like to gracefully acknowledge the funding received over the years for research in this area from European Science Foundation, UK India Education Research Initiative, DIT and DST. Of course, I would love to acknowledge my collaborators at the BCI Lab, University of Essex, England, Cognitive Neuroinformatics Group, University of Bremen, Germany, and my very own lab, the BCR Lab, Computer Science and Engineering, Tejpur University. And I would love to really make it very clear in the very beginning that most of the work that I'm going to talk of today is work done by my PhD scholars, past and present. Therefore, I would like to acknowledge my PhDs, both past and present, for their untiring efforts. Now, before we move on, it is important for us to really understand the terms that I am trying to introduce. Human-machine interaction, and because the whole short-term program that you're attending is on human-centered computing, I do not think it requires any introduction. But then here we are not talking of only the computer and the human interacting. We are taking it one step further to actually really interact with any computational unit that may be trying to control a machine. So our interaction with the human is far beyond just interacting with a computer screen. It is more to do with interacting with control components, which we refer to as embodied cognition. The next term that's very important for us to realize before we move ahead is the term on neurorehabilitation. So neurorehabilitation is a very complex medical process which aims to aid recovery from a nervous system injury and minimizes and or compensate for any functional alteration resulting from it. Robotic neurorehabilitation seeks to incorporate advances in robotics that's combined with neuroscience and rehabilitation to define new methods for treating problems related with neuromotor coordination, evolving novel strategies for motor therapy. Bionic prosthetics, on the other hand, are actually artificial artifacts. In our case, they are limbs that work by using signals from an individual's muscles. That is electromyogram to seamlessly move, and also rely on electrical signals from the brains and nerves, that is electroencephalogram, in order to create human-like movements and reflexes. And all of this effort, the research in this area is poised for restoration of extreme upper limb functions of the human body that's lost due to amputation or stroke. So computational motor control and learning principles derived from study in healthy subjects are introduced in the context of robotic neurorehabilitation. Particular attention is paid to the idea of context, task generation, training. Now, the assumptions that underline the choice of movement trajectories programmed into the robot or the degree of active participation required by the subjects are examined within robotic neurorehabilitation. Neurorehabilitation considers rehabilitation as a general learning problem, and that is where you would see the idea of machine learning coming in. So rehabilitation is seen as a general learning program, and it is examined from the perspective of theoretical learning frameworks such as supervised and unsupervised learning. More recently, reinforcement learning is also being looked at as some form of performing robotic neurorehabilitation. I shall today only cover fundamentals underlying current robotic neurorehabilitation paradigms, and that too from very high-level control strategy perspective. As already stated, neurorehabilitation is a complex medical process, and conventional neurorehabilitation appears to have little impact on impairment over and above that of spontaneous biological recovery. But robotic neurorehabilitation has the potential for a greater impact on impairment due to easy deployment, number one. Number two, its applicability across a wide range of motor impairments. Number three, its high measurement reliability. And number four, the capacity to deliver high dose and high intensity training protocols, which may not be possible with a conventional physiotherapist. So robots are particularly suitable for both rigorous training and application of motor learning principles. But what is more important is they create an environment, an ecosystem for real human-machine interaction, where the machine components are tried to be as cognitively enabled as a human person that is trying to help. And that makes robotic neurorehabilitation so very exciting. Now, there are a number of examples of rehabilitation robots that have been put into practice over the years. Here are a couple of them on your screens. The number A here shows Locomot, which is an exoskeletal robot to manipulate patients' hip and knee. By this time, I believe all of you have got the idea that we are talking of providing physical exercise or mental practice to people who have lost their ability to move these because of disabling diseases or stroke or some other physical conditions. So here Locomot is an exoskeleton to manipulate hips and knees. Number B is the Great Trainer, and number C is again another form of Great Trainer. These are end effector robots, that is, they manipulate the patient's foot. In number D here, we have the Bimanu truck. That's bimanual training of the wrist and the forearm. Here in E, you could see Osaka University's shoulder and elbow robot. And in F, you have Amidio, the one that manipulates individual fingers. Now, why I'm showing you all this is to really enthuse you to the idea that research in biomedical robotic technology is experiencing a huge development in several health domains, particularly in rehabilitation treatment. And this is because of the technological advances in machine learning and artificial intelligence. More robots, or what I would love to call sophisticated mechatronic systems, equipped with powerful processing units, are able to exploit real-time information on the human component for enabling patient-tailored assistance during the exercises to be performed. And in most advanced cases, these robotic machines allow real-time tailoring of each exercise for the whole therapy on the basis of the user's residual abilities. What is referred to in clinical terms as retention of residual skills. So if a physiotherapist was aiding a person, he would not know what would be the minimum capabilities the person could be entrusted with, and will only give the support that's needed. Machines, on the other hand, try to figure that out and try to only provide assistance as required, leading to retention of residual skills. This is through an online assessment of human performance and really tailoring the online motor training strategy. Now, all of these ideas on robotic neurorehabilitation is actually grounded on the relatively recent scientific evidence in neuroscience that physical exercise and spatially action-related movements promote functional recovery, even after traumatic lesions of the central nervous system. And in this, robotic machines for motor therapy play a fundamental role. There are two important types of these machines: the end effector devices and the exoskeletons. End effector devices are one that have a specific interface that mechanically constrain the distal parts of the human limb. On the other hand, exoskeletons exactly reproduce the kinematics of the whole limb and support its movement. So if you have noticed in these figures that I have shown you a little while ago, few of these machines were actually trying to constrain the far end, like the fingers were only supported or the legs were only supported, whereas few other machines were trying to reproduce the kinematics of the complete limb and support its movement. These are the two ways that you could really use robots for neurorehabilitation. Here are a couple of end effector devices: the arm rehabilitation and the leg rehabilitation. Notice that they are only trying to move the distal parts, the end part here, the finger and the hands on your left, and the legs movement on your right. Whereas exoskeleton devices, they support the complete kinematic change. So they try to reproduce the whole joints and the movement patterns. Now, I think this is enough for us to realize that while we are doing this, and we are doing this to an amount that needs to be done minimal, so as the person who has some skills do not lose them, I would need some amount of machine learning or some amount of intelligence, if you allow, to be built into this system. So in this context, researchers have considered many aspects in designing these devices. One aspect is definitely related to the goal of the intended therapy. Another aspect is to take into account the combination of sensory, motor, and biomechanical approaches towards the reduction of abnormal motor responses. So if you look at the functional architecture, you would see that here it is not only about taking mechanical structures and actuating them to move things, but you must read back from the biological system, bring in this sensor data, and try to understand this vis-a-vis some controller. And then that controller should then be able to give you this is minimal support. Given this background from the beginning of my talk today until now, you should have now this perspective why I am here in a machine and human-machine computer interface short-term program. Because this functional architecture on which most of these neuro-rehabilitation robots and the bionic prosthetics that I'm going to talk of in a little while from now work on is through a very integrated human-machine interface that I have marked here in some baby pink color. See, human-machine interface is an important component for I need to really understand by taking some supervisory level control commands from the human, but then my machine system should have enough sensors, including sensing from the biological system that is controlling, to really have a control and supervisor unit that tells me how much of actuation and needs to be done, or what is the type of actuation that needs to be done for a particular task to be accomplished by that neurorehabilitation robot. So the robot capability to accomplish certain tasks or functions need to be carefully considered and analyzed. In fact, robotic design include the type and level of provided assistance, which I should repeat again, should be tailored in order to address the capabilities, limitations, and training needs of the targeted patients. So in order to cope with all these challenges, additional components are these sensors and interfaces to the human body in the overall architecture. And that's something very, very important. Let us now quickly take a look at the conceptual control diagram for such a human-machine interface. So the control diagram, if you want, the conceptual control diagram on the interaction between the robot for rehabilitation and the human being that's being assisted is shown on your screens now. Now, the motion control all in the human body can be simply defined as a feedback loop, where the brain plays the role of controlling the human motion. So the brain controls the muscles to follow an arbitrary designed motion, and let's call that desired motion XD. So the control output UH, which is generated by the brain, is the motor control signal sent to the muscles to produce a joint torque F, and then the input, that's the human motion intention to the robot, can be actually extracted from the human robot interface through some force sensors or muscle related signals. The robot's controller can then command the actuators to generate an assistive torque, FA here, accordingly, which is delivered to the musculoskeletal system, either through an end effector device or an exoskeleton device. And the human body is then actuated, not by its own signals coming from the muscles alone, but from the muscles as well as external actuation via a human-robot interface and external actuators to make some movement on the musculoskeletal system. And then this assistive torque F, A, which is complementing the movement of the muscle force F, generates the total torque Ft, and the system moves. Now the human body can then be again used as a sensor. Like I can take readings from the muscles, the electromyogram signals, or muscle or some other signals to understand how things are moving and put it back. So in other words, the whole idea of a human-machine interaction for movement of muscle systems that have been lost by somebody or that have been weakened for somebody, like in Parkinson's, in other diseases it is tremendously weakened. In diseases such as stroke, it is not there at all. So I can compensate that and make it possible for our robotic devices to bring in that motion. And that is where this idea of using robots for neurorehabilitation holds a lot of promise. This promise has come, you people should realize by this time, because at this point I want to understand what is the human intention by looking at the muscle signals before I send it to the robot controller. And that understanding, I can use traditional machine learning methods as supervised, unsupervised learning to really understand what is the intention so that I can really get that intention clear and actuate accordingly. And that is why there is a lot of progress today in robotic neurorehabilitation. This is partly because of the progress in ML and AI. So when we are talking of such control strategies, there are strategies explicitly designed to provoke motor plasticity, and we call them high level because we are looking at those control algorithms that are explicitly designed to provoke motor plasticity. So for many robots, such high-level algorithms are supported by low-level controllers that achieve the force, position, impedance, or admittance control necessary to implement the high-level algorithm. So research in robotic therapy has advanced the state of art in low-level force control. For example, in control of cable-based actuators. So control algorithms in the idea of robotic neurorehabilitation or human-robot interaction in robotic rehabilitation is grouped into the following: assistive control strategies, challenge-based control algorithms, haptic simulation strategies, and non-contact coaching. There could be other strategies likely to be conceived in the future, but presently almost all algorithms of human-machine interaction for neurorehabilitation falls in these four categories. So the most advanced paradigm within this is the assistive control strategy or the assistive controllers, which help participants to move their weakened limbs in desired patterns during grasping, reaching or walking, a strategy similar to active assist exercises that are performed by the rehabilitation therapist. So it could be impedance-based, counterbalance-based, EMG, and performance-based assistance. I will come to each of them in the course of my presentation. Challenge-based controllers are something that's a new addition to human-machine interaction for neurorehabilitation, where you refer to controllers that are in some way the opposite of assistive controllers. You make movement terms more difficult or challenging. So you provide resistance to the participant's limb movement during exercise. You require specific patterns of force generation or increase the size of the movement error. And these type leads to either resistive strategies, that is increased resistance, constraint-induced strategies, that is you increase the force requirement, or you somehow increase the error amplification. That is, you lead to error amplification. The haptic simulation refers to practice of activity of daily living movement in virtual environments, and the non-contact coaching is about robotic devices that do not physically contact the participant, but instead serve as coaches. They are actually humanoid robots that somehow shows you the physical embodiment, automated coaching mechanisms. Now, all these strategies are not mutually independent, and many of them are combinations. So let us look at each of them one by one. In most of these, if you see, assistive control strategies is what is most important. Okay? Examples of robotic therapies using different types of assistance-based controller are shown on your screen now. Two of the first devices to undergo clinical testing was one shown here in A, the MIT Manus, and in B, the Locomot, which I have shown a little while ago as well. Manus adapts timing and stiffness of the controller based on participants' performance. And Locomot adjusts the size of the desired strapping trajectory based on participants' interaction forces. Then we have Hayward in C. That's a hand robot which uses triggered assistance. And we have in D the T-Rex that uses passive gravity balancing to provide assistance. And in F we have the pneumatic Rex that builds a real-time computer model of the participants' weaknesses and uses it to provide feed-forward assistance. Now, all of these methods actually gives some form of feedback to the system on the person's performance, and the system uses machine learning algorithms to adjust the amount of force that it needs to give to the system. And that makes this system really intelligent. Now, let me quickly take you through one or two of these so that things become more interesting. And I'm not going to the controls of all of them because control would be too difficult to understand in just an hour of talk. But what I really want to make you feel is that the human-machine interaction happening here is real time, number one, and is based on real sensing of either our electromechanical systems or of the human body itself. On your screens now, I have a figure of an impedance controller, which actually gets me the desired force that the robot should apply. From things as position sensors as working on the human body, or force sensors working on the robotic system. So the measured position and is used as an input to an impedance controlling the desired impedance parameters, and the impedance controller generates a desired force, which is the FD, and the desired actuator force and the actual kinematic trajectory are used to control the robot. And as a result, the robot executes the command and applies it on the human. But then the human's own position controller signal again is fed back, and I have a machine and a man working together to get the human system to its desired trajectory. Now, there are other forms of controller which I am skipping: admittance control and different forms of assistance. Now, assistance here, as in any other system, could be a function of time. When I am talking of assistance here for a neurorehabilitation robot, it could be continuous assistance, as shown here, or it could be time-triggered assistance. The one in orange is the patient's voluntary movement. The one in blue is one that the machine takes over. So assistance could be continuous, assistance could be time-triggered, it could be activity-triggered assistance, or pulse assistance, or challenge-based assistance. So note that except for all other assistance, only in channels-based assistance, in contrast to other examples, here the force of the robotic device is less than that of the patient. So the patient needs to exert a force or a voluntary activity that is generally higher in magnitude than exerted by the robot. Now, all of these makes it possible for systems to really work in tandem with the human. Taking it one step further, let me try to give you a little bit example or feeling of how do we get the feedback that I have been drawing in these circuits that I have shown you from the human body. So how does the human sensors really work? So this diagram that I have put is the only complex diagram that I will talk of in the talk. There is no more complex diagram, so take some time to really understand what I mean. Like I told you a little while ago, that the idea is for the robot controller that's sitting here at the center to really adjust its assistance level based on human-machine interaction. But human-machine interaction in terms of sensing coming from the human senses. So either I take muscle signals and get some feeling of how the muscles are being activated given this much assistance, or I take signals from the brain to understand how is motor activity being controlled or happening in the human body to take that assistance. So Neuromotor Recovery, which is about regulation of task difficulty or equivalently the desired or target performance, is implemented by regulating the assistance here. And I provide different forms of assistance by changing the performance of the assigned motor task. So regulation requires a proper estimation of the patient's performance that is done through movement kinematics and kinetics. I measure via human senses how things are moving. So idea behind this concept is to control the motor recovery process through performance-based regulation of the training parameters. We can represent the whole system as shown here through a control loop in which the motor control system of the patient somehow influences the performance of the motor task using the voluntary system. The resulting performance then influences both the motor control system and the real actual robot. And this can modify the amount of assistance and properties of the motor tasks. So this schematic of the performance-based adaptation brings us to a point where we are now pretty close to defining what we do in human-machine interaction for our neurorehabilitation. In human-machine interaction for our neurorehabilitation, we are looking at getting the biosignals, signals from the human body, interact somehow with the robotic devices that aid neurorehabilitation. And we work in signals from the muscles and the brain. So let's have a look at the brain first. So let's focus particularly on neuromotor recovery. So we use electromyogram signals from the brain, particularly from the motor cortex. The motor association cortex, as shown here, which is responsible for coordination of complex motion, and the primary motor cortex, responsible for our initiation of voluntary movement. Now, we collect EEG from the surface of the scalp, which is non-invasive and therefore a preferred option over other invasive techniques. Neuromotor recovery through physical and mental practice is based on a premise, very, very important, called neuroplasticity. Neuroplasticity is about the capacity of neurons and neural networks in the brain to change their connection and behavior in response to new information, sensory stimulation, development, damage, or dysfunction. Now, neuroplasticity is employed by the brain during the reinforcement of sensory information through experience, such as in learning and memory, and following actual damage to the brain. So, brain-machine interfaces that you hear so very much today, these are used in neurorehabilitation to harness the power of neuroplasticity for therapeutic use. So we need to really look at the brain and its core components to understand what we have. So the core component of the nervous system is the neuron or the nerve cell, and neural processes such as those that underline the generation of our movement, they rely on distributed network through the cortical and subcortical brain areas. A neuron is electrically excitable cell that processes and transmits information by electrochemical signaling. And each neuron is connected to about 10,000 other neurons. Now, this is the typical construction of a neuron. So a neuron typically has as a very long axon and consists of a cell body called the soma, and there are dendrites here. At these ends you could see dendrites that typically branch and extend a few hundred micrometers from the soma. Now, as already told, the neuron is an electrically excitable cell that communicates with other cells via specialized connections called synapses. Now, the most important point that I want to make is this motor cortex, MI, the premotor and supplementary motor areas, they contain a subset of neurons that target spinal motor neurons and corticospinal neurons. And functional significance is that This area is specialized to drive fine motor control, such as movement of the fingers, forelimbs, and many other parameters associated with movement. So we are looking at this brain circuitry and trying to really look at this neural circuit, which is a population of neurons interconnected by synapses to carry out specific action. And when I say neuroplasticity, I mean if this circuit is damaged somehow, bring in exercise regimes and try to recreate these circuits again, regrow this. And that happens all the time in your brain, and that is what is affected here. So if you look at the particular ideas that we are looking for are in brain, and you could see that typical electrode placements could be inside the brain, on the surface of the brain, and on the surface of the skull, and outside non-contact. We are interested in the surface measurements of the signals called EEG, which gives enough spatiotemporal resolution, and we are interested in assisting people via understanding their motor function using EEG. So basically this EEG triggered assistance, and what happens is that PCI technologies have started to develop extracting neuro or physiological signals from the brain to control finally certain robotic devices. Now the scientific interest in BCI is corroborated by the fact that they can be used even in the earliest phase of stroke recovery, when the individual human limb is not able to infer movement intention to guide robotic training. But still signals are produced. And that is what makes BCI a very, very important and HCI technology for our neurorehabilitation. Now, signal resolution and the idea of having signals from different portions, and the more invasive is the neural implant, we have higher accessible spatial and temporal resolution. But that creates more problems. And the idea is to exploit machine learning and AI to really use surface EEG and try to get the same amount of intentions that can be captured through invasive. And that is where machine learning and AI comes in. So specific regions are responsible for motor planning. So as you do that planning, increase EEG activities in this area, indicate that some motor imagery is going on. You try to understand that signal, and then you process that signal, get the features, use some translation algorithms to really then command some devices. So once this rehabilitation robot detects the increased EEG activity, it activates assistance along a predefined trajectory. So it's a typical machine learning problem where you have signals coming from the brain, you want to understand these signals and try to classify it to an intention that the robot needs to follow. There are other ways of using signals here for human-machine interaction. And the one that I showed previous was the direct command from the brain to the machine. And we can also think of restoring natural feedback. That is, get sensory receptors, pick up senses, and then via this neurons go to back to the brain. So this type of restoration of natural feedback is also being undertaken within neurorehabilitation. Now let me tell you where we have used it. We have used it in a 5-fingered bionic hand that we are developing over the years. For the last couple of years, we are working on a 5-fingered bionic hand. And we are looking at using machine learning to really understand different movements that the hand can take based on just your EMG signal, the electromyogram signal, and trying to really synthesize a affordable functional prosthesis. Now, this, as I was indicating in all of the talk in the previous example, was about a machine learning architecture. So we really do data acquisition and then do data processing. Thereafter, we create a model and then we execute the thing. So basically, if you look at the machine learning scenario, we are interested in supervised learning, where we look at classification. And our pipeline is about learning to predict some output given an input vector. So basically, we have this 5-fingered bionic hand, which does different grasp patterns or different gestures. And we are interested in understanding how these gestures are happening. So in order to do this, we go for an optimization of the design parameters, look at what are the different components in the human hand that can be copied into the design. And that's a different story. That's called biomimesis. So we copy the human hand first into the biomechanical hand. And then what we do is more interesting for us for today's talk. We try to really understand how the human hand is being controlled from signals coming from the brain via the spinal cord reaching the muscles. So we look at these muscles, the flexor capri ulnaris muscle, the flexor digitorum muscle, the extensor digitorum muscle, the extensor capri radialis longus muscle. We look at these muscles and try to understand the EMG signal coming there, take that EMG signal, acquire that, and then follow a simple pattern recognition pipeline to really understand what is the type of grasp this person is trying to emulate. Remember that this person does not have the hand, or even if he has the hand, he does not have the ability to move the hand any longer. All he has the ability is to send the EMG signals. So he somehow sends the EMG signals, and we capture them to really understand what type of interaction is he expecting, what is his intention, and try to follow this. So it's like a simple pattern recognition pipeline where you take the signal, you do the processing, classification, and you try to get this idea of what is the signal that it is doing. So why I'm trying to emphasize this is that I want you to take home this point that the ability of human-machine interaction has been pushed as farther. This limits of doing human-machine has been put farther by improvements in machine learning. Had we not made so much improvement in machine learning, the idea of machine in human-machine interaction would have been very rudimentary. Today we could do things like interfacing a electromechanical system to completely a human body and putting it there as a natural replacement of its natural part, only because of this improvement and in machine learning. So I will not do this machine learning portion here possibly. I will skip the machine learning in support vector machine in that we have used and try to concentrate on what we are doing in terms of human machine interaction. So I'll not talk of how we do the simple classification of the human grasp intentions. We use a simple supervised machine learning system, a support vector machine. Okay. The next thing that we is doing and very important for human machine interaction is haptic feedback. So if you look at the feedback system that we have in our human body, you have mechanoreceptors in the skin that sense the external stimuli, and then these external stimuli, it goes to the peripheral nervous system, and from the peripheral nervous system, the sensory signal takes it back to the central nervous system. So the idea in haptic feedback is to really recreate this is environment vis-a-vis the human brain interaction, so into electromechanical systems. So in spite of much progress in the world of bionic prosthetics or exoskeletons that I have shown you in the beginning of the lecture, or in human-machine interaction, there remains a lot of things to be achieved in terms of the feedback system, where mechanoreceptors in the skin can pass information to the central nervous system. We have started to look at this. When I say we, I mean in not just my lab, but people in neuro rehabilitation have started to look at this, where sensors on the prosthetic hand or a neuro rehabilitation robot collect the tactile information, and then it does signal encoding to pass it on to some external stimulators that are then activating the actual peripheral nervous system. So either I could have non-invasive external stimulators as activating or stimulating the PNS, or I could have invasive direct stimulation of the PNS, and this can simply follow the natural path to the sensory signal. Now, the only area where machine learning has to be used is about trying to understand the senses reading vis-a-vis this activation potential to be generated. Once you can do it, you can then have sensors that can tell me, artificial sensors that can tell me if I am feeling hot, cold, or hard, or smooth, or rough surfaces. So this is very exciting technology that's coming in for human-machine interaction. And in a way, then there is this idea of so I have then this idea of motor imagery from the scalp. So we have looked at this and seen that motor imagery from scalp EEG could be used for human-machine interaction. So motor imagery from scalp EEG for human-machine interaction has been used. And how does one use motor imagery? Let me give you some idea. So what we do is we ask certain people to only imagine in picking up things or fisting or taking a glass, and then these are classified to see what type of motor imagery system is being used. Motor imagery is being done. Now, this has led to a very interesting interaction architecture, which is about putting the signals from the brain and the signals from the muscles together. So we have this idea of electroencephalogram, signals from the brain, and electromyogram, signals from the muscles, and these two together can bring in what are called hybrid adaptive control via what is called corticomuscular coupling. So the signals from the cortex, the motor cortex that I have discussed a little while ago, and signals from the muscles, they have a correlation. If I can get that correlation properly, then I can really understand my intention coming from the brain and the intention that is finally reaching my muscles. Okay? So you could have EEG being captured, and then you could look at selected features from that EEG telling me what is his thought process about movement of his fingers. You could collect signals from the muscles that I have named a little while ago and really understand what is the muscle signal that is trying to move the fingers. So both of these together could then come to a superior control or negotiator, which would then negotiate between the brain signals and the muscle signals. And then this negotiation would be passed on by the mediator to a local control. Your local control means controlling the electronics, okay? Lower level electronics. So it is really passed on to a controller. It could be a PD, PID, or what type of controller you have. So it passes on to the real time low level controller, and that controller then takes action to move the fingers. Now what is happening here is that a person who has the ability to move his fingers, who do not have the ability to move his fingers, but still can send muscle signals. So his neuromuscular link is not over, or he can send signals here and that can take help. Whereas people who have lost that ability, but only retains the ability to generate thought processes, as the machine will work or by just taking the human intention. People who have both, but to a reduced level, one will compensate the other, and we will have a good control. So the EEG-EMG hybrid adaptive controller is about two things. One, people who have the ability, they are allowed to do things the way they want. People who do not have the ability, assistance is provided to them, amount required, leading to, number one, the retention of residual skills. Number two, providing assistance as required. And these are two very important concepts for our recovery in neurorehabilitation. Fine. So the next thing that we have observed is that once people have motor imagery, people think a lot using their brain, and prolonged motor imagery actually leads to mental fatigue. So you tend to get tired. So if you are really looking at interaction between a man and a machine, and you are thinking that you'll use a BCI, you will have to do some form of imagination by the brain. That brain imagination that is referred to as motor imagery, if you imagine moving your hand, do not move your hand, but just imagine moving your hand, that's called motor imagery. So we have seen that prolonged motor imagery induces mental fatigue. You get tired. And that mental fatigue then deteriorates the motor imagery EEG signal, making it impossible for the original classifier that you have designed, let's say, for the EEG classification of human intention does not work any longer. So you need some form of characterization of motor imagery vis-a-vis mental fatigue. So such analysis has rarely been done in the literature. There is only recent realization that yes, BCI is a good stuff, but then BCI can give you fatigue, and this fatigue deteriorates EEG signals, and therefore we need some form of adaptation in these circuits is a recent realization, and this needs to be done. So monitoring fatigue while performing motor imagery holds the promise to have and adaptive brain-computer interface. And that is something which my lab has been looking very closely. So we have looked at motor imagery mental fatigue via a very interesting algorithm called the KPLS-based monitoring. I will not go into what KPLS is, but it is a regression method, a kernel Purcell least square based regression method, where you first look at the kernel Purcell least square maximum relevant, minimum redundant feature set. So you look for a set of features that are maximally relevant and minimally redundant, leading to the best feature vectors for fatigue analysis. And then you monitor the change in fatigue level using these coefficients of the kernel Purcell least square. And then you estimate the growth of fatigue as you do motor imagery. And finally, you analyze the effect of mental fatigue on motor imagery from a signal feature perspective. So let me show you how some of the subjects, we had done this study on some 11 subjects, real subjects, and we have seen that as you ask them to do different motor imagery, so there are these runs here means they have been asked to do prolonged motor imagery for half an hour each run. So as you do a lot of motor imagery, what happens is the mean of the KPLS score, that is a measure of fatigue, it increases. Okay, so motor imagery. So what does this tells us? This tells us that motor imagery actually gives mental fatigue, and we have extensive mental fatigue if we do extensive motor imagery. So we have looked at the topographic plots or topographic maps of this. So these topographic plots depict marked increase in the delta, theta, and alpha power. These are rhythms of EEG that either rises or goes down when you do think of movement. So this was the first run. You could see that the dark color increases as I go towards the last run. So the dark red color in the topographic map that I show you here indicates increasing in delta, alpha, and theta power, and the green zones encompass those electrodes which were not used for this analysis. So we could see that the dark color depicts the highest value of delta, theta, and alpha, and this figure clearly portrays the increase in these rhythms from the first to the last run, with fatigue reaching the highest level during the last run. So here it is the most darkest in the last run, which is towards your right. So, and then another interesting thing that you see is the frontal areas is found to be mostly affected with the rise in fatigue level. So now you can correlate this with your own life. So this is the nose, okay? This protrusion is the nose. So as you get tired, the front of your head, the temporal region, and so the frontal area here that you have, the frontal area is found to be most affected with the rising fatigue level. And delta power is found to be more prominent. And the delta power is found to be more prominent here. So this shows that motor imagery produces increased levels of drowsiness and decreased level of arousal. Therefore, any intelligent assistive device that I can think of that uses motor imagery, it must be adaptive, else its performance would deteriorate over time. And that adaptation has to be made in this. And that we have done via a very simple algorithm of linear regression. Now let me take a couple of minutes to tell you what linear regression is. Linear regression is best suited for problems where attributes and labels are all numeric, and there is reason to expect that the linear function will approximate that problem. So we have used linear regression and to study how mental fatigue and motor imagery correlate. And in linear regression, you have the concept of an independent variable, a variable whose value does not change by the effect of other variables. And then we have the dependent variable whose value changes when there is a manipulation in value of the independent variable. So what we have done is we have looked at this problem of fatigue and motor imagery and mental fatigue, and tried to find out some form of a relationship between these variables. Like here in this example, I show you a relationship between in the cumulative grade point that you get at the end of your 8th semester exam while you are studying, and what would be your starting salary. Now, there is nothing new here. Linear regression is possibly one of the oldest forms of machine learning and is a long-established statistical technique that involves simplifying a line to some other data. Why I am talking of this is I'm trying to bring home the point that machine learning needs to be looked at for its application, not by really picking up whatever is the hype, but by looking at things that are already there in the machine learning repertoire and trying to understand and how you could use them for the current problem at hand. So we use a simple linear regression model where the equation describes how y is related to x, and we get the two parameters, the slope of the line and the y-intercept, and we are able to get the relationship between mental fatigue and motor imagery. I will not go into all of this, but I will still emphasize that all we have done is got the correlation between them and tried to understand this. To really finally look for an unsupervised learning method to get to the idea of really adapting the BCI. So an unsupervised learning method is about creating an internal representation and without any external intervention. So we look at this idea of common spatial pattern, which is about finding out a filter for the different motor commands from the motor cortex in terms of EEG, and trying to separate the plus from the circles here in the example. After the CSP filtering, the idea is that the pluses will be along the S1 coordinate system and the blues will be along the S2 coordinate system. And this is what we do. So we take up this idea of unsupervised common spatial pattern to update a common spatial pattern filter by tracking the fatigue level of the user. Now, this is based on updating a covariance matrix. I'm not going into the details of this, but basically what I'm trying to emphasize is that you could really create an adaptive common spatial pattern. That is, you could have a CSP, ordinary CSP, which does not gives me enough ideas of how fatigue is happening or what is the signal. But once I do an adaptation based on mental fatigue, I get stronger signals. And then I should be able to decide how to adapt my robot that's doing neuro rehabilitation. So basically, this leads to the idea of the brain-computer interface for our robotic neurorehabilitation not only as a sensor. It does only not act as an actor. Most of the BCI that you see in human-machine interaction is about the BCI being used only as an actor. You see a signal coming, you get the intention, you move things. What we have done beyond that is also use the BCI as a sensor to get a sense of the human well-being when he is trying to act or control a device using his brain signals. So the BCI here is used both as a sensor and as an actor. And then, the most interesting part is that there is this mediator which tries to understand the command coming via the BCI's actor role and the adaptation required coming via the BCI's sensor role, and mediates between the control module and the adaptation module to really understand what type of control has to be from the manual side and what type of control has to be from the pre-designed automatic module. So the mediator decides based on the fatigue or the sensory signals coming from the brain, if all of the control could be passed to the manual side, or none of the control could be passed to the manual side, or what is the percentage of control that he will give to the manual controller, and how much will be done automatically. And all of this is done seamlessly. So the person controlling the device has no idea that he is not controlling it. Rather, the machine is controlling it. He has this well-being, feeling of well-being, that yes, I am able to control my hand. That gives him enough confidence to build his confidence. He then tries to do some very difficult maneuvers, but then that is not possible, and that the automatic controller module takes over. So this idea of using the brain as a sensor and the brain as an actor, together with a mediator that mediates between manual and automatic seamless control change, is based on the idea of cognitive architectures. So the automatic control module is actually trying to create a cognitive model at the same level of a human brain. And that ensures that this transfer from manual to automatic or from automatic to manual, or this combination of these two, is happening in such a way that the man controlling the device has no idea that he is not controlling it. That builds his confidence, that retains the residual skills, and the whole control is only providing assistance as required, the minimal assistance as required, driving neurorehabilitation to its extreme level. And that is what makes human-machine interaction a very important area to look at within neurorehabilitation, because these ideas could then be transported into real clinical practice. To finally wind up my talk, numerous efforts have been made in neurorehabilitation driven through advances in control and robotics, particularly in human-machine interaction. Advances in human-machine interaction has been possible because of advances in AI and machine learning, which have enhanced assistive control to embrace adaptation based on physiological responses from the human body directly. Strategies still need to be further evaluated, and these strategies need to be put into clinical practice. Many of this, which I have shown you, are part of clinical practice. Many of these are still laboratory trials. But at least the neurorehabilitation robots that I have put for you have been put into clinical practice. Rehabilitation robots or robotics neurorehabilitation needs to be augmented further with high-level decision making and cognitively enabled human-machine interaction algorithms. And this is something that is an upcoming research area. If you are yet to pick up a PhD topic, this is something that you should really think of doing. Cognitively enabled human-machine interaction for high-level decision-making in neurorehabilitation. Combination of novel AI methods, better computational models of motor learning and recovery. These will finally leverage the therapeutic advantage of rehabilitation robots. And this would possibly lead to their wider adaptation in many different settings. Right now, all that neurorehabilitation robots are used for is used in stroke rehabilitation or only in bionic prosthetics after amputation. There are other areas where it holds a lot of promise, like tremor suppression in Parkinson's diseases, or exoskeletons or exoskeletal devices in arthritis. So there is a lot of scope for human-machine interaction between a man and a real electromechanical machine, rather than just as an algorithm running inside a computer. And with that, I end my talk. I emphasize on all of you young people to take up human-machine interaction and for really taking robotics, AI, ML, for healthcare and well-being of people who have lost their abilities, is of having a quality of life. Thank you very much. If there are any questions, I would be happy to take them. Hello?
Participants, you may ask your questions.
Great. There doesn't seem to be any questions there, Dr. Mehdi. So, yeah.
Yes, sir. Yes, sir. Most probably there are no questions. In the comment box also there are no questions as such. So,
Great.
Sir, thank you for your provoking talk, and it was a great experience to hear from you. And thank you, sir, for your time out of your busy schedule that you accepted our invitation and given us the opportunity to learn from you. And from the HTC team and Department of Electronics and entire Guwahati University family, I would like to thank you for your time and for your informative talk. Thank you, sir. Thank you very much.
Thank you, and have a nice day. Thank you very much. Can I leave the meeting now, Dr.
Yes.
Mehdi?
Yes, sir. Definitely, sir. Thank you, sir.
Thank you very much. See you later.